Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the previous lectures, we have studied the theoretical basis of modal analysis. In these and the next lectures, we are going to now study signal processing for modal analysis. So, what is the need of signal processing in modal analysis, or what kind of signal processing needs to be carried out to carry out modal analysis? The first motivation is basically the estimation of FRFs, right. So, let me write down. Signal processing for modal analysis. Okay. So, for experimental modal analysis, FRFs are basically the fundamental inputs which are processed in order to obtain the modal parameters of the system, right. And FRFs we have defined earlier as the ratio of the response and the force in the frequency domain, right. And what we measure basically the response and force signals, they are nothing but the time domain signals, and then these signals need to be transformed to the frequency domain to find the FRF. So, that is one motivation for signal processing, right, FRF estimation. Okay. The other issue also which is relevant here is that in practice the signal that is recorded is in discretized form, okay, and then therefore what we have got is a discrete time signal, and the frequency domain representation of a discrete time signal or is to be carried out in order to find its frequency domain representation. So, therefore, another issue which also is relevant and we will study is the digital signal processing of the signals. Okay. So, discrete or digital signal processing of signals. Transformation of a discrete signal into frequency domain is also associated with certain pitfalls, and then we should avoid either or eliminate or minimize the errors which are associated with that. So, those are also few things we are going to discuss in this in the next lecture. Therefore, good understanding of signal processing and discrete signal processing is required to ensure that we are able to interpret the results correctly and the measurement errors are avoided in the process. So, now we are going to first look at today the processing of continuous time signals. So, the theory of processing of continuous time signals basically can be used to develop the theory of discrete time signals. So, therefore, let us first define what are continuous time signals. Okay. And by the way, what is a signal, right? A signal basically conveys information as a function of some independent variable, right. A signal conveys information as a function of some independent variable, right. And a continuous time signal is the one where time is the independent variable, okay, and the signal is defined at every instant, okay, and that is why it is referred as a continuous time signal. So, in continuous time signal, the independent variable is time, and the signal is defined at every instant, right. For example, the acceleration of a vibrating structure is a continuous time signal, right, because the acceleration exists at every instant of time. So therefore, the continuous time signals can also be simply referred as continuous signals, and they are also called as analog signals, right. So we can simply refer continuous time signals as continuous signals for simplicity, or we can also call them as analog signals. Okay. So let us classify continuous signals. Classification of continuous signals. So we have continuous signals like this, okay, and then we have the continuous signals can be either periodic or aperiodic. All right, and the periodic signals can be either harmonic or non-harmonic. Okay, and aperiodic signals can be either transient or finite length signals. Or it can also be random. So random is a signal is another kind of aperiodic signal, correct. So what is a periodic signal? What is a periodic signal? A periodic signal is the one which repeats after a certain length of time, right. So if I take this signal for example, so this signal is repeats after time capital T. So this signal X repeats after time capital T. So we can therefore say that if x of t plus n times t is equal to x of t, right, for where n is an integer. Okay. So if x of t plus n t is equal to x of t, then it means that the signal is repeating after every integer multiples of length t. The periodic signal can be harmonic or non-harmonic. So what is a harmonic signal? So a harmonic signal is one in which the second derivative of the signal with respect to time is proportional to the signal itself and is negative of that, right. So if x of t is the signal, then the second derivative with respect to time is x double dot t. This can be written as minus say omega square x of t, right. So when the signal can be satisfies this equality, then the signal is a harmonic signal and the frequency of the signal is omega. So sine and cosine signals, sine and cosine functions or signals, right, are basically harmonic signals. because that is Wallis property, right. But some signals which are periodic may not necessarily be harmonic, right. For example, if we combine two harmonic signals of different frequencies, right, then it gives a periodic signal, but that signal is no longer harmonic. Okay. So, therefore, non-harmonic signals, they are periodic, but they are not harmonic. Then we have transient signals or signals which are of finite length. So, such signals basically exist for some finite length of time, and after that they do not repeat, and hence they are aperiodic. Similarly, the random signals. So, random signal is a signal which varies in a manner which is not predictable, or it is not as per any deterministic law, right. So, such signals proceed for an indefinite length of time, and such signals also do not repeat, and hence these signals are also aperiodic. So, now we are going to focus attention on in this lecture we are further going to talk about now the frequency domain representations of periodic signals. Fourier analysis can be used to carry out the frequency domain representation of periodic signals, and Fourier analysis is a very crucial tool for signal analysis, and this can be applied to a signal of any nature. Of course, in the modal analysis we will be concerned with signals like acceleration signal, velocity signal, displacement signal, force signal, or voltage signals. Okay. But of course, this is Fourier analysis is widely used in many areas of science and engineering. So, let us look at first of all Fourier series representation or expansion, okay, in the trigonometric form. So, let us look at the Fourier series expansion of continuous periodic signals, and we are going to look at the trigonometric form of the Fourier series expansion. So, if we have any signal which is periodic, let us say if we have a periodic signal x of t, okay, and let us say the period of the signal is capital T, okay. So, T is the time period of the signal in seconds. So, we define frequency called as fundamental frequency represented by omega naught, which is nothing but 2 pi upon T. So, as per Fourier series expansion, this signal x of t, it can be represented as a sum of sine and cosine signals whose frequencies are integer multiple of the fundamental frequency, right. So, we can write the Fourier series expansion as x of t is equal to a naught plus a n cos n omega naught t with n varying from 1 to infinity plus b n sin n omega naught t with n varying from 1 to infinity, right. So, here on the right hand side we have cos and sine functions, right, and the frequency of these functions is n omega naught, right, and if since n is an integer, the frequencies of these different harmonic components, they are basically integer multiple of the fundamental frequencies, and a naught here is basically DC component. Okay, it is a component which is constant, which does not change with time, similar to the DC voltage, right, which is constant. So here if we try to represent this expansion graphically, then it basically can be shown like this. So we have this periodic signal, okay, and now we are representing it as sum of a constant component which is A naught like this. Then we have cost components. The cost components, the first cost component is A1, so it varies like this. So amplitude of this component is A1, right. So this is A1 cos omega naught t. Then we have the second component, okay, and the frequency of this component is twice that of fundamental frequency. So it completes 2 number of cycles in the time period t in this manner. So this component has amplitude A2. So in this manner we have all the cos components, and then we have also the sine components, right. So if we plot this, so the first sine component is having amplitude B1 and it completes 1 cycle in the time period t like this. So this amplitude here is B1, and then we have the component with amplitude B2 and it completes 2 number of cycles in the time period of the signal signal x of t. So this amplitude is B2. So in this way there are infinite number of such components in general. So this is basically what is Fourier series expansion, where the periodic signal is broken down into a sum of harmonic signals. So all these sines and cosine signals here, they are harmonic signals, okay, and they are related to the their frequencies are related to the fundamental frequency by an integer relationship. So here the coefficients A1, A2 up to A infinity and B1, B2 up to B infinity and A naught, they represent the strength of these individual components in the signal. That represents the contribution of these components to the original signal. Now the question is, how do we determine these coefficients, right? How to find these coefficients? So here we use the orthogonality properties of these sine and harmonic functions, orthogonality properties of harmonic functions. So if let us say P and Q are non-zero positive integers, okay. So it can be shown that the integral of say cos P omega naught t into cos Q omega naught t into dt, right. This basically we can simplify using trigonometric identity and write this as cos P plus Q omega naught t plus cos P minus Q omega naught t, right. So if you carry out this integral, then both these integrals would be 0, right, for p not equal to q. So, if this p and q are two distinct integers, then the integral of the both these cost terms would be 0, right, because say if we talk about cos p plus q omega naught t, then this signal will have p plus q number of cycles in the time period capital T of the signal, right, and integral of all these cycles basically would be 0, right, because integral here corresponds to the area under this curve, cosine curve, and we have the positive and negative areas, they would basically add up and cancel each other. Similarly, we can show that integral of sine p omega naught t into sine q omega naught t dt over 0 to t, this also actually is 0, right, because we see that this is nothing but cos p minus q omega naught t minus cos p plus q omega naught t, right. Again we have two cosine terms here. So, again integral over one time period over the time period t, this will be 0 for p not equal to q, right. If p is equal to q, then cos p minus q would be cos 0 t, and cos 0 t integral is not 0, right. And if we have integral of sine p omega naught t multiplied by cos q omega naught t, okay, this can be written as sine p plus q omega naught t plus sine p minus q omega naught t, right, and now this integral is 0 for any choice of p and q, correct, because here we have sine function. So, even if p is equal to q, still sine 0 omega naught t would still be integral would be 0, right. So, these are basically referred as the orthogonality properties of the harmonic functions, okay, and now we can utilize these results to find the coefficients in the Fourier series. So, let us try to first determine the Fourier coefficient r, AR, right, which is the coefficient of the term cos r omega naught t. Let us determine that what is the value of this coefficient. So, to determine this, what we do is that we multiply both sides, right, of the Fourier series expansion by cos r omega naught t, right, and we integrate the two sides over one time period, right, that is what we do. So, if we do that, what is going to happen? We will have cos r omega naught t dt from 0 to t, right, and here we will have now a naught plus a n cos n omega naught t with n varying from 1 to infinity, plus we have b n sin n omega naught t with n varying from 1 to infinity, and this is multiplied by cos r omega naught t, right, and then of course we need to integrate this over 0 to t. So, we see that if based on the orthogonality properties we got, all the integrals right in this series would be 0 except the integral in which rth term in the series involving the cosine functions, right, that integral will not be 0. So, here we would be left with only one integral, which is AR cos r omega naught t into cos r omega naught t. All the rest of the integrals would be 0 because of the orthogonality relationship, and if we simplify this, then basically what we get is this result, that we have 2 by t integral 0 to t of x of t cos r omega naught t. Okay. So, this is the result we get for AR. Similarly, we can determine BR. Okay. So, for this we multiply both sides by sin r omega naught t, and we integrate the both sides over 0 to t. So, if we now do that, then again we would notice that only the term involving sin r omega naught t, right, in the summation series, that would not be integrated to 0, and all the rest of the term would be integrated to 0. And after simplification we get this result, that BR is equal to 2 by t integral 0 to t x of t sin r omega naught t dt. So, in this way we get the coefficient BR, and of course here by varying r from 1 to up to infinity, we can basically obtain all the coefficients, right. What about A naught? So, A naught is basically a constant term which might be present in the signal. So, for this we can simply integrate both the sides from 0 to t. Okay. So, if we do that, then we get this result. So, all the cos and sin terms would be integrated to 0. Okay. And we would be left only with the A naught term on the right hand side, and hence the integral the result for A naught is this 1 upon t integration 0 to t x of t dt. So, this also can be looked upon simply as the mean value of the signal, right. It also represents the mean value of the signal. So, in this way we can basically determine all the Fourier coefficients. Okay. We can also present the Fourier series expansion in an alternative trigonometric form. Okay. So, Fourier series expansion, we can also represent it in an alternative trigonometric form, right. So, so we have basically the sine and cosine components of same frequency. So, those that pair of sine and cosine we can combine using trigonometric equations, right, using trigonometric formulas we can combine them and write or merge into a single cosine term with some phase difference, right. So, we can write the Fourier series expansion in this form also, x of t is equal to A naught plus some new coefficient dn cos and omega naught t minus theta n, with n varying from 1 to infinity. So, this is an alternative form of the Fourier series expansion. So, here dn of course is related to the an and bn, right. By dn would be simply square root of an square plus bn square, and similarly theta n would can be determined from an and bn, the phase lag. So, here what we see that the on the right hand side we have now the frequency components whose amplitude basically is given by dn. They have the frequency n omega naught and their phase is theta n, right. So, therefore, now let us define what is frequency domain representation and time domain representation. So, what is time domain representation of a signal? So, time domain representation is the representation of the signal right as a function of time. Okay. So, the left hand side of the above equation is nothing but the time domain representation of the signal. Okay. And what is frequency domain representation? So, the frequency domain representation is the representation of the signal in terms of the frequency, amplitude and phase of different harmonic components or signals, right, which make up the signal. So, that is nothing but the frequency domain representation. So, the right hand side of the above equation basically is the frequency domain representation. So, here on the right hand side we have harmonic signals, and each harmonic signal is described by its amplitude, its frequency and its phase lag. Okay. So, now this frequency domain representation can be formally presented either in the tabular form, in which we tabulate the values of the frequencies, their amplitude and the phase, or we can also present it in a more convenient form, a graphical form, right. So, that graphical form of presenting this frequency domain data basically is referred as Fourier spectrum, a set of two spectrums, right. So, graphical presentation of Fourier analysis, right, that is basically referred as Fourier spectrum. Okay. So, here we have now the, for every frequency component we have the amplitude of the component and the phase of the component, and that is why we require two such plots to represent the magnitude or the amplitude and phase. So, the first plot is called as magnitude spectrum, right, and the magnitude spectrum in the magnitude spectrum we plot the frequency on the x axis, and the frequency in this case the frequencies are all discrete components, okay, integer multiple of the fundamental frequency component omega naught, 2 omega naught, then we have 3 omega naught, and we have 4 omega naught and so on, okay, and then we can represent the magnitude of the components here, right. So, A naught is a component with 0 frequency. So, if there is any mean value of the signal there or any DC component in the signal, then that will be appearing here as a non-zero component, right. And then we will have a component, we can have a component at omega naught, then some component might be there at 2 omega naught, 3 omega naught and so on. So, this is just a typical plot which may be resulted after the Fourier analysis. So, on the of course, here we are plotting the amplitude of the component, which in the present case we have represented by dn. So, this is nothing but a magnitude spectrum, and then we also have another one, phase spectrum, where we represent the phase of these different components, right. So, here of course, this is omega x frequency axis, and so we have omega naught, 2 omega naught, 3 omega naught and so on. So, then we have this phase spectrum. So, this phase again can be there, and this is just a typical phase plot which might be there. So, here we have the phase which is nothing but theta m. and it could be in degree or radian. Let us say it is in degree, right. So these are the two spectrums. So another thing to be noticed is that these spectrums are line spectrums, okay, they are line spectrums, because the frequency components, they are present at discrete frequencies, correct, as the frequency components are present at discrete frequencies. For example, we have a component at omega naught, and then at 2 omega naught, and then at 3 omega naught, but there is no component between them, okay. So the frequency components related only by interrelationship are there. So what is the advantage of frequency domain presentation? Advantage of frequency domain representation of a signal. So one important advantage is that it basically gives an insight into what harmonic components or frequency components which make up the signal, right, and that information can provide vital clue about the origin or source, or the sources or the origins which are giving rise to those components, okay, and that may help in the diagnosis of the the source responsible for generating those components in the signal, right. But on the contrary, in the time domain, it's a time domain plot from where we can understand that how the signal is varying, what is the amplitude of the signal, but that does not give easily, or rather it does not give an idea of what frequencies might be present in the signal, okay, especially when large number of frequency components are present. So time domain representation does not give much insight into what signal consists of, but the frequency domain representation gives an indication of what are the constituents, components which make up the signal. So then how many for the continuous for the analysis of continuous signal, how many frequency components are required? Because we see that in general the summation runs from 1 to infinity. The components or the infinite components might be required in general to represent the signal in the frequency domain. So of course that would be true if we want to have a very exact representation of the signal in the frequency domain. But then in the practice we will be forced to use finite number of components, and therefore the number of components which give adequate representation of the signal, okay, or a representation which is reasonably accurate, those many components should be retained in the series, right. And how can we test that the components being taken are adequate? So we can do a reconstruction of the signal using the chosen components, okay. So we can substitute back the values of the amplitude, frequencies and the phases on the right hand side right of the Fourier series, and we can reconstruct the signal based on those components, and then we can compare that reconstruction with the original signal, and if the reconstructed signal is close to the original signal, then we can go ahead with that representation, right. So that is how we can decide the number of frequency components that might be required in the Fourier series representation of a continuous signal. Let us now look at the complex form of the Fourier series. Complex form of the Fourier series. So this form is essential, and it is important for the reason that we are going to use this form to develop the frequency domain representation of continuous aperiodic signals and discrete signals. Okay. So, this result we are going to use later as well. So, in the complex form of Fourier series, we can use Euler's identity to represent the sine and cosine harmonic signals. So, we know that the cos n omega naught t, it can be written as e to the power I n omega naught t plus e to the power minus I n omega naught t upon 2, right. And then we also have sine n omega naught t, it can be written as e to the power I n omega naught t minus e to the power minus I n omega naught t upon 2I, right, which of course if I multiply by I in the numerator and denominator, so what do I get? We get e to the power minus I n omega naught t, right, minus e to the power I n omega naught t I divided by 2. So, let us substitute these expressions in the trigonometric form of the Fourier series. Let us go to next page, and now we can write down x of t is equal to a naught plus summation from n is equal to 1 to infinity, and then I have a n, and then in place of cos n omega naught t I can write down e to the power I n omega naught t minus e to the power minus I n omega naught t divided by 2, right, plus summation n to is equal to 1 to infinity b n, and then I have I e to the power minus I n omega naught t minus e to the power I n omega naught t divided by 2, right. So, in this way we have substituted the expressions for cos n omega naught t and sin n omega naught t. Now, if you take e to the power I n omega naught t common from the two those series, then the coefficient would be a n minus I minus I b n by 2, right, plus with n varying from 1 to infinity, and then we have again another sum from n is equal to 1 to infinity. Now, I have the coefficient of e to the power minus I n omega naught t, and that coefficient is sorry, I think I made a small error here. This should be plus here, right? In this equation there should be plus. So, then what do I get? A n plus I b n by 2. This is what we get. And now, let us represent a naught, right, by say some variable c n c naught. Let us represent it by c naught, a naught, and now this is we can call as c n e to the power n omega naught t, n varying from 1 to infinity, and we have n is equal to 1 to infinity. This is nothing but c n star. So, this is nothing but the complex conjugate of c n e to the power minus I n omega naught t, right. We can further write down this as, so we can multiply this by e to the power I rather 0 omega naught t, right, because I to the power 0 omega naught t is nothing but 1 plus n is equal to 1 to infinity. This is same c n e to the power minus e to the power I n omega naught t plus. Now, this we can write as n is equal to minus 1 to minus infinity, right, and this we can write as c n e to the power I n omega naught t, correct. So, the minus sign in the power of exponential we have transferred to the limits, okay, and therefore, this is the result. So, here we should note that C naught is actually A naught and C minus N, okay, or C minus R is equal to complex conjugate of CR. So, now we can combine these three terms into a single sum with n varying from minus infinity, okay, to plus infinity, because we have the exponentials e to the power I n omega naught t, and here n is varying not only from 1 to infinity, but also from minus 1 to minus infinity, and also for n is equal to 0. So, that is why all these three these three terms can be merged into a single series sum with Cn e to the power I n omega naught t. So, therefore, this is the final result we have. So, this is another form of the Fourier series expansion, and this is called complex form. Complex form of the Fourier series, and since we started from the trigonometric form by and then we converted that to this form using Euler's identity, both these forms are equivalent, okay, they are mathematically equivalent. This is just another alternative way of presenting the Fourier series. So, here the Cn, they are nothing but the complex Fourier coefficients. So, what is Cn here? Cn is nothing but they represent complex Fourier coefficients. Right. So, this series basically presents or represents the periodic signal as sum of complex exponentials, right. So, e to the power I n omega naught t is a complex exponential function, right, and Cn is the amplitude of that function. So, when we combine also exponential functions with n varying from minus infinity to plus infinity, we are essentially combining these complex exponentials in order to represent a signal x of t. So, now how we determine the complex coefficients, how to find CR, that is the complex coefficients. So, here we can multiply both sides by e to the power minus I r omega naught t, right, and integrate over one time period of the signal. So, when we do that we get this result. So, now we have 0 to t, and then we have the summation from n is equal to minus infinity to plus infinity Cn e to the power I n omega naught t multiplied by e to the power minus I r omega naught t into dt, correct. So, on the right hand side all the terms, the integration of all the terms except n is equal to r, right, that would be that integral would be 0, right, the all the those integrations are going to be 0, right, because this e to the power I exponential function also consists of cos and sine functions, right, and if the frequency of those functions is non-zero, the integration of all those both the harmonic functions will be 0. So, therefore, here we are simply left with integration of 0 to t Cr into 1 into dt, that is all, that is what we get, and this would be nothing but Cr into t, and hence we get the expression that Cr is equal to 1 by t integral x of t e to the power minus I r omega naught t dt from 0 to t. So, this is the expression we get for the complex Fourier coefficient. So, the result of the complex Fourier series can be represented in the frequency domain by giving a plot of the magnitude of the complex Fourier coefficient and the phase of the complex Fourier coefficient. So, we get what we call as complex Fourier spectrums. Okay. So, we can give the magnitude of the component, say Cm, as a function of frequency, and the frequencies would be omega naught, 2 omega naught, 3 omega naught, like this, and we also have minus omega naught, minus 2 omega naught, minus 3 omega naught, and so on. And this spectrum would be symmetric with respect to the magnitude axis, right. So, the magnitude of the omega naught and minus omega naught component, they would be equal. Similarly, the magnitude of the 2 omega naught and minus 2 omega naught components would be equal. So, this is a typical plot that may result, and so this is the magnitude spectrum. And we will also have phase spectrum, phase of Cm. So, here again we will have positive frequency components, 2 omega naught, 3 omega naught, 4 omega naught, and minus omega naught, minus 2 omega naught, minus 3 omega naught, minus 4 omega naught, and so on, right. And now this plot will be asymmetric, because the complex Fourier coefficients for r and minus r, right, they are complex conjugate, and because of that their phase difference would be having a difference of 180 degree, because of which the phase spectrum would be asymmetric. So, let us say if the phase of the component omega naught is say 90 degree, let us suppose, then the phase of the minus omega naught component would be minus 90 degree. So, they will have phase of 180 degree difference, right. So, in this way the phase plot will be anti-asymmetric. So, this is one way to present the complex Fourier spectrums. An alternative way is to present them as the real and imaginary parts of the complex Fourier coefficients. So, we can have the real part of Cn, okay, as a function of frequency, and then we can have imaginary part of the Cn as a function of frequency, okay. So, again here we will have both frequency components, positive and negative. So, the real part of these components, they are equal, because the components are complex conjugate, while the imaginary parts are negative of each other. So, it will be asymmetric with respect to the imaginary axis. So, now we can raise a question here that in the complex form of the Fourier series, we have complex exponentials appearing on the right hand side, while on the left hand side the signal x of t is real. It is a real life signal, so it has to be real. So, how is it possible that a real signal is being represented by complex exponentials, right? So, how do complex exponentials make up a real signal? To understand this, let us look at a pair of exponentials corresponding to frequency frequency r omega naught and minus r omega naught. Okay. So, let us look at the exponential I r omega naught t whose amplitude is C r, right. Let us look at this component first. So, this is basically can be looked upon as a vector rotating in the complex plane. So, if I take this complex plane, here we can show the real part of the vector and here we will show the imaginary part, right. So, this is a vector, okay, and what is the magnitude of what is this vector? So, if we write down, because CR is complex, so we can write this as CR, right, into e to the power minus I theta naught, okay, into e to the power I r omega naught t. So, we can further write this component as CR e to the power minus I r omega naught t, right, minus theta r, sorry, let us call it theta r, okay. So, we can write this in this form. Now, this can be represented here as a vector whose length is CR, right, and which is rotating at a frequency r omega naught in the clockwise direction, right, in the anti-clockwise direction, okay. So, this is nothing but the vector CR e to the power I r omega naught t minus theta r. So, this vector is CR e to the power I r omega naught t minus theta r. Similarly, we can look at the vector C minus r e to the power minus I r omega naught t, and by following the same process we can represent this as magnitude of C minus r e to the power minus I r omega naught t minus theta r, right, noting that the magnitude of C minus r is same as that of CR. So, this is a vector which is rotating in the clockwise direction, right, its magnitude is same as that of CR and it is rotating at a angular velocity r omega naught, but in the clockwise direction, and this vector is nothing but C minus r e to the power minus I r omega naught t minus theta r, right. So, these two vectors are there which are simultaneously there, and if we combine them by law of vector addition, then these two vectors would be combining and resulting into a vector this, right. So, let me use this color. So, we get this vector, right. So, when we combine we get this vector, and this vector is nothing but 2 CR cos r omega naught t minus theta r, right. So, the result is that the combination of these two exponential vectors which correspond to frequency plus r omega naught and minus r omega naught, they together make up a real signal, because there, as we see from this vector diagram, the resultant of these two vectors is a vector which is along the real axis and it does not have any imaginary component, okay. So, these two exponentials together represent or make up a real signal, and that has been possible because now along with the positive frequency r omega naught, we also have a negative frequency minus r omega naught, and therefore, these two frequencies, positive and negative frequencies together make up a real harmonic frequency, and that is why we see that in the complex Fourier spectrum, the spectrum exists not only on the positive frequency side, but also exist on the negative frequency side. So, we have positive frequency axis and negative frequency axis, but in the trigonometric form of the Fourier series and the Fourier spectrum based on that, we had only the positive frequency axis, right. So, the existence of positive and negative frequencies in the complex Fourier spectrum are needed in order to represent a real signal using the complex exponentials. So, in this way today we have looked at the frequency domain representation of continuous periodic signals, and now I think we can stop here. Thank you.